common practice is to apply only 80% of a breaker's rating as the maximum continuous load. Circuit breakers are designed to trip when the current reaches 100% of their rated capacity, but consistent overloading can damage them or even cause them to fail prematurely. Staying below 80% helps to ensure that the breaker will trip safely in the event of a fault and can extend the breaker's lifespan. The National Electrical Code, or NEC, addresses this issue in several sections. NEC Section 210.20 states that branch circuit overcurrent protection devices shall be rated for not less than 125% of the continuous loads, plus 100% of the non-continuous loads. This is another way of stating the 80% derating requirement for continuous loads. This requirement is in place because circuit breakers, especially those of smaller ratings, can be significantly affected by heat. A breaker carrying its maximum rated current continuously will heat up, and this heat can cause the breaker to trip prematurely or even damage the breaker over time. The 80% rule helps to mitigate this risk by reducing the amount of heat generated by the breaker. An exception to the 80% rule exists for non-continuous loads. A non-continuous load is defined as a load that is not expected to operate for 3 hours or more at a time. For these types of loads, the breaker can be loaded to 100% of its rating. The breaker will have sufficient time to cool down before reaching its rated capacity. Examples of non-continuous loads include space heaters, air conditioners, refrigerators, freezers, pumps, and compressors. However, keep in mind that even though individual appliances may cycle on and off, the overall load on a circuit can still be continuous if the combined operation of multiple devices exceeds the 3I threshold. When determining whether a load is continuous, it is essential to consider the specific application and the expected operating conditions. If there is any doubt, it is always best to err on the side of caution and apply the 80% rule. Several factors can influence the appropriate breaker size and load calculations. Firstly, ambient temperature plays a significant role. Circuit breakers are typically rated for operation in an ambient temperature of 40 degrees Celsius, or 104 degrees Fahrenheit. If the ambient temperature exceeds this value, the breaker's current carrying capacity may need to be derated. Secondly, the number of conductors in a raceway or cable also affects the allowable ampacity. When multiple current-carrying conductors are bundled together, the heat generated by each conductor can raise the temperature of the other conductors, reducing their ability to dissipate heat. In these cases, the conductor ampacity must be derated according to NEC Table 310.15. 3. Thirdly, voltage drop is another critical consideration. Voltage drop occurs when the voltage at the load is less than the voltage at the source due to the impedance of the conductors. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. To minimize voltage drop, it may be necessary to increase the size of the conductors. Circuit breaker selection also depends on the type of load being served. For example, motors can draw a large inrush current when they start, which can trip a standard circuit breaker. In these cases, a time delay circuit breaker may be required. A time delay breaker is designed to withstand the inrush current without tripping, but it will still trip quickly in the event of a sustained overload or short circuit. Another important aspect of circuit breaker selection is the interrupting rating. The interrupting rating is the maximum fault current that a breaker can safely interrupt. It is essential to select a breaker with an interrupting rating that is greater than the available fault current at the point of installation. The available fault current can be calculated using various methods, including short circuit studies. If a breaker is subjected to a fault current that exceeds its interrupting rating, it can fail catastrophically, potentially causing significant damage and injury. Furthermore, arc flash hazard is a serious concern in electrical systems. An arc flash is a dangerous electrical explosion that can occur when there is a fault in the system. Arc flashes can generate intense heat pressure waves and flying debris, posing a significant risk to personnel. To mitigate arc flash hazards, it is essential to implement appropriate safety measures such as wearing personal protective equipment, or PPE, and using arc flash rated equipment. Arc flash studies can be performed to determine the potential arc flash hazard levels in a system, and this information can be used to select the appropriate PPE and implement other safety measures. Ground fault circuit interrupters, or GFCIs, are another critical safety device used in electrical systems. GFCIs are designed to protect people from electric shock by detecting ground faults and quickly interrupting the circuit. A ground fault occurs when current flows through an unintended path to ground, such as through a person's body. GFCIs are required in many locations, including bathrooms, kitchens, and outdoor areas. They work by monitoring the current flowing in the hot and neutral conductors of a circuit. If there is a difference of 5 milliamps or more between the two currents, the GFCI will trip, interrupting the circuit and preventing electric shock. Arc fault circuit interrupters, or FSIs, are designed to protect against fires caused by arc faults. An arc fault is an unintentional electrical discharge that can occur when there is damaged or deteriorated wiring. Arc faults can generate high temperatures, which can ignite nearby combustible materials. FSIs are required in many locations, including bedrooms and living rooms. They work by monitoring the electrical waveform for characteristics that are indicative of an arc fault. When an arc fault is detected, the FSI will trip, interrupting the circuit and preventing a fire. In addition to circuit breakers, fuses are another type of overcurrent protection device. Fuses are designed to melt and open the circuit when the current exceeds a certain level. Fuses are available in a variety of types and sizes, each with its own specific characteristics and applications. Time delay fuses are designed to withstand momentary overloads without opening, while fast-acting fuses are designed to open quickly in the event of a short circuit. Fuse selection depends on the specific application and the type of load being served. Coordination studies are often performed to ensure that the overcurrent protection devices in a system are properly coordinated. Coordination means that the overcurrent protection devices closest to the fault will trip first, minimizing the extent of the outage. Coordination studies involve analyzing the time current characteristics of the overcurrent protection devices to ensure that they will operate in the desired sequence. Selective coordination is a more stringent requirement that ensures that only the overcurrent protection device closest to the fault will trip, even under worst-case fault conditions. Proper grounding is essential for electrical safety. Grounding provides a low-impedance path for fault current to flow back to the source, allowing the overcurrent protection device to trip and clear the fault. Grounding also helps to stabilize the voltage in the electrical system and reduce the risk of electric shock. The NEC specifies detailed requirements for grounding electrical systems, including the size and type of grounding conductors, the methods of grounding electrodes, and the bonding of metallic components. Bonding is the process of connecting metallic components together to create a low impedance path for fault current. Bonding is essential for preventing voltage differences between metallic components, which can create a shock hazard. The NEC requires bonding of all metallic components that are likely to become energized, such as metal conduits, enclosures, and equipment frames. Surge protection devices, or SPDs, are used to protect electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, switching operations, and other electrical disturbances. SPD work by diverting the surge current to ground, protecting the equipment from damage. SPD are available in a variety of types and sizes, each with its own specific characteristics and applications. They are typically installed at the service entrance and at other critical locations throughout the electrical system. Electrical codes and standards are constantly evolving to reflect new technologies and best practices. It is essential to stay up to date on the latest codes and standards to ensure that electrical systems are designed, installed, and maintained safely and effectively. The NEC is the most widely adopted electrical code in the United States, and it is updated every 3 years. Other relevant standards include those published by the Institute of Electrical and Electronics Engineers, or IEE, the National Electrical Manufacturers Association, or NEMA, and Underwriters Laboratories, or UL. Proper electrical safety training is essential for all personnel who work on or around electrical systems. Electrical safety training should cover topics such as hazard recognition, lockout/tagout procedures, personal protective equipment, and safe work practices. Qualified electrical workers should receive more in-depth training on electrical theory, code requirements, and troubleshooting techniques. Regular refresher training is essential to ensure that personnel maintain their knowledge and skills. Electrical inspections are an important part of ensuring electrical safety. Electrical inspections are typically performed by qualified electrical inspectors who are employed by local governments or other organizations. Electrical inspections involve verifying that electrical systems are installed in accordance with applicable codes and standards. Electrical inspectors may also identify potential hazards and recommend corrective actions. Regular electrical inspections can help to prevent electrical fires, shocks, and other electrical accidents. Electrical maintenance is essential for ensuring the continued safe and reliable operation of electrical systems. Electrical maintenance should include regular inspections, testing, and cleaning of electrical equipment. Electrical maintenance tasks should be performed by qualified electrical workers who are trained in safe work practices. Proper electrical maintenance can help to prevent equipment failures, extend the life of electrical equipment, and improve the overall safety of the electrical system. When working on electrical systems, it is essential to follow lockout/tagout procedures. Lockout/tagout procedures are designed to prevent accidental energization of electrical equipment during maintenance or repair. Lockout involves disconnecting the equipment from its power source and attaching a lock to the disconnect switch. Tagout involves attaching a tag to the disconnect switch, warning others not to energize the equipment. Lockout/tagout procedures should be followed whenever working on electrical equipment that could be energized. The 80% rule is a general guideline and may not be applicable in all situations. It is essential to consult the NEC and other applicable codes and standards to determine the specific requirements for each application. If you are unsure whether or not a load is continuous, it is always best to err on the side of caution and apply the 80% rule.